SNF for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process, from assisting screening and reservoir studies, polymer logistics, to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. Polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.
Hello, everybody. My name is Rafaela, and I am the webmaster of this SP Unicamp student chapter. And today I will be the moderator of this course. First of all, I would like to remind you that our second Kahoot quiz game is available now, and we will end at 7 p.m. Brazil time. The prizes are incredible, so it's worth participating. Check the chat or email and access the link to play. The game pin is 03507 943. Before Before I start, I'd like to make a few remarks to the audience. All opinions in this event refer only the opinions of the speakers and participants and not of their respective companions or even the captor. Furthermore, if there is any allusion of a discriminatory nature or reference to social, gender, or racial discrimination, the participant will be aware that he will be immediately notified. Don't forget to send your doubts and questions on chat. The guests will answer. Sorry. Then at the end of the presentation. For those who intended to obtain the certificate of the course, at the end of the session, a form will be made available to confirm the presence. Certificates will be issued to those who obtain 75% attendance according to the form. And finally, don't forget to follow us on Instagram, SP Unicamp, so you can follow our activities in addition to having access to quality information. So now we will present our guest. Aaron Burton is a mechanical engineer with several years of hands-on field experience with multi-stage completion tools and techniques in numerous unconventional formations around the world. Broad-based experience of asset life cycle, including reservoir propriety, directional drilling, stimulation design, and correlation of each service. Recognizing tool leaders live and training courses, publishing technical literature, and participating in many host industry events. In-depth knowledge and experience of unconventional markets, capable of capturing business, market plans, and strategies to gain market share in existing and emerging markets. Welcome, Errol, and feel free for make your lecture.
All right, well, thank you. Thank you, everyone, for organizing and everyone for attending. So just to confirm real quick, let's see. Can you see my screen, see my presentation here?
Yes, we can see.
Okay,
Yes.
perfect. You can hear me and everything else well?
Yes, the sounds great.
Okay, great. All right, yeah, so this is a course on multi-stage completions for hydraulic fracturing. So just before we get started, a couple of quick things. So, it's a limited time that we have, so you can go to my website and check out UOG training or UOG.training. So if you want to see, I've got a video blog there, some free training courses, paid training courses as well. But if you want some additional information to review this material, you can go there, and also have a YouTube channel as well. So if you type in my name on YouTube, you should be able to find my channel and see segments of this course, as well as other material not covered in this course. And it's also worth mentioning too. So I am a full-time employee with Morph Packers, so not necessarily applicable to this presentation as we are focusing on the completion side. But now I'm focused in my full-time job as with refract products as well. So we focus on liner refracts. So we'll start off with kind of what is a shale? What is it? What are these unconventional plays? So this is actually the definition from geology.com. I won't read this to you, especially those of you that are reservoir engineers. You probably can explain it better than I can. But really what I'm getting at here is shale is a type of rock. So if you hear people in the States talking about these plays, a lot of times you'll hear them call them shale plays. In reality, it doesn't have to be a shale. It doesn't have to be a shale type of rock. So when people slangly say shale, what is shale? What they're referring to is a low permeability formation, typically less than 5 millidarcies for oil. It's a consolidated formation, so you don't have to worry much about sand control, sand fines, things like that. And they can be shale rock, but they can be sandstones, carbonates, dolomites, whatever out there. What they're actually referring to is a reservoir that requires multi-stage hydraulic fracturing to be able to produce at economical rates. So the name of the game in these wells are increasing the reservoir contact area. So you can drill a vertical well in these formations. and get exposure to that formation. But generally speaking, most of the plays, especially in the U.S., are no thicker than about 500 feet thick. So very minimal thickness that you can access with a vertical well. So you could drill that vertical well, you could get access to that portion of it, but if you take this, let's just call it that 500-foot thick targeted reservoir, if you drill a horizontal well in it and drill it out 5,000 feet, 10,000 feet, maybe even 15,000 feet, now you've really significantly increased the contact area for that horizontal well. So, like I said, it's very thin in the U.S., but then if you go into some of the international markets, there are some thicker reservoirs. So, for example, in certain sections in the Vaca Muerta in Argentina, it can be up to 5,000 feet thick or so. And initially, the thought process was they might could do a vertical well development there instead of a horizontal well development. However, once they tried their vertical pilot wells, started multi-stage fracturing through them, what they realized is just the different rock properties, the different bedding planes, the different issues or inconsistency in rock in that vertical well actually created some problems. So they actually kicked off a horizontal well program as well. So even though not technically a requirement for the well to be horizontal, at least all of the international or worldwide plays that I know of that are in these types of plays, it does seem to be that horizontal wells are at least a better option from a production standpoint, from a fracturing and access to the reservoir standpoint. And then the same thing with multi-stage hydraulic fracturing. We can take that vertical well, we could place multiple stages of hydraulic fractures in it and increase that contact area. But now if we take this 5, 10, maybe 15,000 foot lateral and put 30, 40, 50 stages accessing further and further away from the wellbore, now we've significantly created a lot of contact area within that formation. So we'll zoom in here just to in the formation. If you're not extremely familiar with completion tools, don't worry too much about the dynamics here yet. We'll cover a lot of that. But what we're looking at here is we've got our light gray, that's our casing. We've got our dark gray, that's our cement. And then, of course, we've got our target reservoir. Now, in this, we've already created perforations. So we've perforated through the casing, through the cement, and now have access into the target reservoir. So we pump our hydraulic frac job, we create fractures, and then we pump sand through them to hold it open. So if we zoom in a little bit further, as we apply the pressure, we create the fracture, and we lead in with our pad fluid. So this is going to be a clean fluid system. You're cracking the rock and moving throughout the formation. Then we pump our slurry, which has our proppant in it, and that's going to, now the fluid is pushing that proppant into the formation, into the fractures you've created. Once you're done fracturing, you bleed off pressure. That formation is going to try to close on itself, and the proppant stays in place and holds that fracture open, which creates your artificial permeability, also known as your conductivity. So now you have those channels to produce your hydrocarbon through. So hydraulic fracture treatment objectives, we're going to create that artificial permeability, also known as conductivity, so that we can produce them. And we might be creating new fractures or reopening existing natural fractures, depending on the situation. We're going to install proppant to hold the fluid flow path open. And we're going to increase the reservoir contact area away from the near wellbore as much as possible. So we drill the well in the direction where transverse fractures will grow from the wellbore. And then we're going to fracture at high rates, pressures, and volumes. So why are the multi-stage completions required? It's because fractures will grow the path of least resistance. And those can be created by drilling stresses, drilling damage, friction losses throughout the well. And this was experimented with a lot in these formations. It's called a barefoot completion. You just drill an open hole, place one large frac down it, and see where it goes. The problem here is that now you've got most of the well accepting most of the treatment, or excuse me, a small portion of the well accepting most of the treatment, and the rest of the well getting little to no treatment. So you're not getting that fluid and proppant distributed throughout that wellbore. You also have to worry about formation weakness, even in that horizontal well. I mentioned in the vertical well, definitely have to worry about it, but even within the horizontal section, you're going to have different stresses as well. Same thing. If you come into this issue, then your fluid and proppant is going to go to the path of least resistance, and you'll have just a small section of the well treated, with the rest of the well with little to no treatment. So that's why we divide the well into compartments called stages. So instead of trying to place one big frac job down it, now we're going to break it up into stages and fracture those stages one at a time to get better distribution of your fluid and proppant throughout that lateral. So there's 3 types of completions that have been proven the most effective and the most efficient in these types of application, and we'll look at those. That's going to be plug and perf, ball activated completion systems, and coil tubing activated completion systems. So with plug and perf, we've already got our initial well drilled. We go in with the drilling rig, with the drilling rig, we install our casing string. Once we've installed that, we're going to pump cement through the casing string into the annulus between the casing and the reservoir, and we're going to cement that casing into place. So if we zoom into the toe, in this case, we've cemented ourselves into place. We can no longer pump into the reservoir. So you have to have tubing conveyed perforating to access the toe. So on a workover rig or a coil tubing unit, you run perforation guns in, you perforate the toe of the well, and then once you're done, pull out a hole with your wellbore intervention tools, and you can begin fracturing through those perforations you've created. Now, as you can imagine, that's takes a lot extra time, some extra expense with those workover tools. And so the technique is not used very often anymore. What most operators do is they replace those toe perforations with some sort of cementable pressure-activated sleeve that they'll make up to the casing and run in the well and cement in the well just like the casing. And then when they're ready to begin fracturing, they just apply the right amount of pressure. The sleeve will open and you can begin fracturing that way. Or they'll run what's called a wet shoe, where basically they design it to where the cement here at the toe does not set up. So they'll put sugar in it or some sort of cement inhibitor. And then now you can still pump out of your toe into the formation to pump down any wireline assembly that you might have. So like I said, it's it's not very often that they do rely on the through tubing intervention to do the toe perforations anymore. Once you get past the first stage, most of the time the process looks the same. Because you have that first stage perforated and fractured, now you have flow through that stage, and now you can switch to a wireline assembly. So of course that will consist of wireline. At the toe of the assembly will be your frac plug. Above that will be your setting tool, and then you'll have your perforation guns above that. So once you pump it down to the intended depth, you send an electric signal through your wireline. That'll activate your setting tool, set your frac plug, and the setting tool releases from the frac plug. So now you can move your wireline assembly up the wellbore. You pull up hole to the depth of your first perforation, another electric signal is sent, and that fires your first set of perforation guns. Pull up hole to the depth of your second set of perforations, another electric signal sent, and that fires your second set of perforations. Pull up hole to the depth of your third perforation, another electric signal will fire that third set of perforation. So and then you would just do that process until you fired all your perforations. So in this case, we only have 3 perforating guns. So the nomenclature here, each perforation is considered a cluster. So this would be 3 clusters per stage would be our design here, since we only have the 3 perforation clusters in the stage. So once you finish perforating, you're going to pull out a hole with your wireline. You're going to set up your frac crew, and you begin fracturing that second stage. Then you're just going to repeat that process. Once you're done fracturing, you shut down your frac crew, you pump down a wireline assembly, set your plug, perforate your third stage, pull out a hole with your wireline assembly, and then begin fracturing your third stage. Then shut down, run a fourth plug, perforate a fourth stage, and go in and out of the well. So this has always been the Achilles heel, the weak point of plug and perf, is that you do have that time in between stages where you shut down your frac crew, run in your wireline assembly, pull out your wireline assembly, and then fracture your next stage. But there's been a lot of efficiency improvements on that we'll discuss later, called simultaneous fracturing. So once you're finished fracturing, a traditional plug-and perf are composite frac plugs. So you go in with a coil tubing unit or a workover rig. You mill out your frac plugs, and at that point, you can put your well on production. So let's talk about the fluid distribution through those clusters. So we'll stick with the 3 clusters per stage example. Basic theory of hydraulic fracturing, we're assuming that we get even distribution through those clusters. So if we're pumping 90 barrels a minute at surface, then we're assuming that we're injecting 30 barrels a minute per cluster and that we're getting that even fluid distribution. Now, the reality is that just because of friction losses, a pretty simple thing, then just that distance means that your fluid distribution is going to look something more like this, because your fluid has less friction to exit the top set of perforations versus the bottom set of perforations. So you'll get uneven distribution there. Now, and just to clarify, this is very simple examples, easy to understand visuals, but it gets a lot more complicated than that because there's a lot more other factors besides friction. There's reservoir properties, there's perforation erosion, a lot of different things. But like I said, this is just to get the concept across to you of the distribution and the limited entry perforating and these types of things. So just an easy, clear-cut example, just making some assumptions here with limited entry perforating. So we'll change the number of holes per cluster. So at the bottom perforation, we'll have 5 holes, middle, we'll have 4, and the top set of perforation, we have 3. So now from a fluid distribution standpoint, a path of least resistance standpoint, it's actually easier for the fluid to exit out of this bottom stage because there's more flow area and more difficult for it to flow out of the topmost, the heelmost perforation because there's less flow area. So the idea with limited entry perforating is to try to balance out the amount of energy it takes to for the fluid and proppant to exit each set of perforation and at least hopefully get even fluid distribution throughout your stage there. Now, once again, this is a simple example. A lot more detail goes into it as far as erosion, reservoir, things like that. But this is a good starting point for understanding what limited entry is. But, like I said, heterogeneity of the formation is an issue. So we'll jump it up to 6 clusters per stage now. What happens if your fracture is breaking down like this because of just the weaker points in the rock being at those 2 stages? So that's where a technique called diverters come into play. So with the diverters, we're trying to divert the fluid, get better distribution of the fluid and proppant through each cluster. And the simplest way to visualize this is to just assume that all of your fluid and proppant is going out of one set of clusters. So you would pump the amount of fluid and volume that you wanted to pump into that cluster, followed by diverters. These are near wellbore diverters. So you'll pump those down. It'll block off those perforations near wellbore and force the fluid to divert into another cluster. You pump the amount of fluid and proppant volume that you want for this cluster and follow it with yet another diverter, blocks off the near wellbore, forces the fluid to divert to another perforation. And then you just repeat that process until you're finished fracturing that stage. So it depends on which kind of diverter you're using. It might be that you have to go in and do an intervention trip to remove the diverters, but there are also some dissolvable ones as well. So that after you finish your diverter job, or your frac job, I should say, those diverters will dissolve in the wellbore fluids and you begin producing your well. But it's, like I said, that's simple to visualize. That's the simplest strategy that you could use. But let's go back to this example here with uneven distribution to begin with. So what happens when you use diverters here? So let's say it works like it's supposed to. Now you've blocked off that that path of least resistance here, and it forces fluid to divert elsewhere. But where does it divert to? That's the question. So what happens if you pump your diverter and it actually does the opposite of what it's supposed to and blocks off a non-producing zone? So that's, like I said, that's exactly the opposite of what you want. Now you're not stimulating that zone for sure, because you've blocked it off temporarily. And then you also have to be sure that you don't pump too much diverter, because then you put yourself in a situation where you screen out and you can no longer pump into that well until at least the diverter is dissolved, or you do some sort of through tubing intervention. So there's a SPE magazine, the JPT article on diverters. It's a great article talking about, I believe it was 5, maybe 6 case histories and different results with different operators. So it's a good article to kind of give you an idea of some of the variabilities and unknowns with the diverters. So why do we use cluster perforations to begin with? It's kind of complicated, a lot of guesswork involved in it. And technically, we could do single entry plug and perf. Go in and fire a single perforation, plug, single perforation, fracture, plug, and then repeat that process. And the reason we do that, or that we don't do the single entry plug and perf, is for efficiency purposes. So this comes from a prominent U.S. operator from their Q1 of 2016 presentation to their investors. And in that presentation, they reported that they had 9,000-foot laterals, 100-foot per stage, with 15-foot cluster spacing. So just a reminder for anybody who's not extremely familiar with the nomenclature. So when we say 100-foot per stage stage spacing, that's 100 feet from this plug to this plug, from this plug to this plug. 15-foot cluster spacing is going to be 15 feet between each cluster of perforations in that stage. So we take that information, and that means that we have 90 stages overall in the well, 6 clusters per stage, and that's 540 total injection points in the well. So now you have 540 individual perforation clusters in that well that you're trying to fracture out of. So if we assume 2 hours of downtime between stages so that we can run our wire line, set our plug, perforate, pull out a hole with our wire line, if we broke it into 90 stages, then that would be 180 hours or 7.5 days, assuming a 24-hour crew of downtime alone, just to run your plug and perforate. If we tried to break that into 540 individual stages, you would be looking at 45 days of downtime alone, not including the frac job. So it would be very, very inefficient to try to do it in a single stage type of manner. So we'll stick with that 540 injection point example and look at a couple of options we could complete it. We could do 180 stages with 3 clusters per stage, and the wireline time that it would take to just run the plug, perforate, pull out a hole, that'd be 15 days. 90 stages with 6 clusters per stage, that would be 7.5 days of wireline. Or 45 stages with 12 clusters per stage, and that would be 3.75 days of downtime. And this is also assuming that 2 hours per stage that we looked at before. Now, with all of that, we also have additional cost savings of 180 stages would be 180 plugs, 90 stages would be 90 frac plugs, and 45 stages would only require 45 frac plugs. Now, one of the primary ways that efficiency has really improved with plug and perf is simultaneous fracturing operations. So what we're looking at here is we're looking at a bird's eye view of 2 laterals. So if you're standing on surface, you look down at your toes, your laterals would be going out away from you. So with the simultaneous fracturing, they bring out a wireline crew, and keep in mind these wellheads are close enough together, so they've kind of gone into pad drilling mode. They're drilling these well bores close together, especially at the wellhead level, and they can go in, bring a wireline crew in, set them between 2 wells, and bring a frac crew in and set them up between the 2 wells so that they can operate both wells without ever having to move the frac crew or the wireline crew. So you would go in and do your perforating. You would start fracturing on well A while you're doing operations on well B, and then you switch the services over. So on well A, you're running your wireline operations, while on well B, you're fracturing. Then you swap back over. So you're running wireline on well B while fracturing well A, and then switch it back. Wireline on well A while fracturing well B. And you're just going to repeat that process. So the way this was set up, you set up your frac crew, and you've got a manifold where you just turn a valve to control whether you're pumping to well A or to well B. And so you never have to do that. You just turn a valve to swap the wells. And with the wire line, it's just a matter of swinging your crane from well A to well B and back to well A. So now instead of having just your frac crew completely idle while running wireline, you're running wireline on another well while your frac crew keeps going. And this can be applied on a large scale. So you can do it with multiple crews even. So if you want to be, if you've got multiple crews, you're fracturing certain wells while running wireline on other wells, and then you just continue switching those services over. So so overall, this really helps drive efficiency with plug and perf by eliminating that downtime between stages in the wells. So some operators actually report that they've optimized this process to the point where they've eliminated the non-productive time between stages. So they always have a wireline truck running, they always have a frac crew running, and they're never sitting there idle in between stages. And another technology to look at with plug and perf is the disintegrating frac plug. So everything we've talked about right now, you have to go back in, mill out afterwards because they're made of composite materials. With this plug, it has the same functionality of the composite plugs, but now it's made of disintegrating materials. So you get it in the well, you set the plug, you pump the ball downhole to isolate on the plug, and then once you're done fracturing, over time, the wellbore fluids and temperatures will dissolve both the frac plug and the frac ball, and it'll remove itself from the well without having intervention, and there'll be a full production diameter in that well. So there are a handful of operators, and it depends on the play and it depends on the cost and things like that. But some of them do run full well bores. But there are still plenty of operators that do more of a hybrid system, where they'll do composite plugs within the range of coil tubing mill out and disintegrating plugs towards the toe of the well outside of the range of coil tubing. So they can go in, mill out the composites with coil tubing, and then over time, the disintegrating plugs will remove themselves from the well. So another technique is the ball activated completion systems. So with the wellbore overview here, we've got our open hole packers isolating the annulus between the casing and the reservoir. We've got our ball activated frac sleeves in between. That's going to be our method of diversion in this system. And a secondary component is the casing packer. So you can use a variety of different packers here as long as it holds the weight of the completion and the temperatures and pressures needed during the frac job. You're pretty flexible with the casing packer. The nomenclature here, it's going to be stage 1 at the toe, working your way back up towards the heel. And there's a couple of setups. So the first one we'll look at is the fluid activated packers. So our open hole packers are fluid activated in this scenario. So once we get to the intended depth, we're going to pump our activation fluid into the annulus. We'll set our casing packer. And then over time, do your pressure testing at that point, and you can move your drilling rig off a location. Over time, these packers will activate and they'll swell out to contact the reservoir, and that's what gives you your annular isolation in this application. Once you're ready to begin frac, you drop a ball in the well, pump it down to the toe sleeve, and then apply pressure, shift that sleeve open, and you can begin your frac job. Now, if we we zoom in here on the second sleeve, overall these sleeves are very simple at least from a conceptual standpoint. So you've got your sleeve made up to your casing, you've got your fracture ports on the sleeve, and if we look at a cutout view, we have an insert with a ball seat profile covering up those frac ports. So as you're fracturing your first stage, you're pumping all of your fluid and proppant through that ball seat. But it's covered up the frac ports so it doesn't go out into the wellbore. And then once you're finishing up your first stage, you drop the ball that corresponds to that second sleeve. It lands on seat, you apply pressure, shift the sleeve open, and begin fracturing your second stage. So once the insert shifted, now your frac ports open, your ball and ball seat isolate from the previously fractured stage, and then your packers on the annulus side isolate from above and below. So there's our above isolation. So now we move up to the third sleeve as we're finishing fracturing our second sleeve, or second stage. Drop the ball that corresponds to this sleeve, apply pressure, shift the sleeve open, and you can begin fracturing your third stage. That's a little bit difficult to tell in the animation, but each of these balls get incrementally larger as you're moving up the well. So the smallest ball will be at the toe of the well, the largest ball will be at the heel of the well. And then it's just a continuous process. Drop the next ball that corresponds to the fourth stage, pump it down hole, apply pressure, shift the sleeve open, begin fracturing your fourth stage. Drop the ball that corresponds to the fifth stage, pump it down hole, apply pressure, shift the sleeve, and fracture. So this is really the highlight of this type of system. It's nonstop fracturing operations. You just have to drop the next ball in the system once you're finished as you're finishing fracturing the previous stage, and then just continuous pumping operations from there. So our post-frac operations with these, you produce back through, of course, the fractures that you've created, back through the ports that you fractured through. And you also have production from the bottom that'll push that ball off seat and up the wellbore. So in a lot of cases, those frac balls are actually disintegrating material as well. So if there's not enough velocity to push them to surface, they will eventually disintegrate in the frac fluids. And you can technically have this as an interventionless system for post-frac, but if you do that, then you are going to be producing through a restricted diameter through all the ball seats that are in the well. These are made out of a cast iron material in most cases and easy to mill out. So if that is a problem, that restriction is a problem, then you can go in, mill out those ball seats relatively easily, and then get a full or near full wellbore diameter. So another option with these sleeves, I presented that they're mainly used in open hole, but you can also use them. They're in cemented applications as well. So there are cemented versions. So what you can do is your wellbore construction looks similar, but now instead of having open hole packers, then you just cement into place so that you have annular isolation through the cement, and then you fracture just by dropping balls. So the fracturing procedure looks exactly the same. The wellbore construction is just a little bit different. And now our final completion system, the coil tubing activated system with frac sleeves. So there's a couple of ways to set this up, but the primary way here is with frac sleeves. So once you've finished drilling the well, you'll run a casing string in with the frac sleeves made up to that casing string. Once you're in place, this is designed to be a cemented system. So you pump cement into the annulus, cement the sleeves and the casing in place. And then once you're done with your cement job, you can do your pressure testing and move your drilling rig off the location. Once we're ready to get fracturing, we're going to run coil tubing into the wellbore and locate our toe sleeve. So our assembly will consist of a coil tubing packer and a sand jet perforator. So sand jet perforator is optional, but in a lot of cases it is run as a contingency, and we'll see why in just a minute. So you run your system in the well, you open the first sleeve, fracture it, move up hole with your coil tubing, locate your second sleeve, open it, and begin fracturing. And then you just repeat that process, moving up the wellbore toe to heel, fracturing each stage. So the benefit of having a sand jet perforator in place is if you're in the middle of a frac and you decide you want to add a stage between this sleeve and the sleeve above it, then you can pull up hole to the depth you want to add the stage, sand jet perforate through the casing, through the cement, and access your target reservoir that way. And then you can add a stage on the fly during the frac job. So if we zoom in on the coil tubing fracturing operations, so as you're pulling up hole, you're going to locate that frac sleeve. You'll set your coil tubing assembly. You'll apply pressure. So once your packer is set into that, once your packer here is set into the insert of the sleeve, then you apply pressure, and that translates it into mechanical force, shifts that frac sleeve open, and now you've exposed your frac ports. So once you've opened the sleeve, now you can begin fracturing. So you're going to pump your fluid and proppant through the annulus of the coil tubing and the casing, out of those frac ports and create your frac job for that stage. So this is because you are pumping between the annulus of the coil tubing and the casing. A lot of times you'll hear people refer to this technique overall as annular fracturing as well. So if you hear annular fracturing, it's some sort of technique very similar to this technique. Once you're done fracturing, you unset your packer, move up the well bore, and locate the next sleeve. Like I said, these were originally designed as cement completions to begin with, but it's very easy to convert them to an open hole completion as well. Just insert your open hole packers between the sleeves, and you can isolate your annulus that way. So with each completion system that we've covered so far, and this is the core of the completion system, each of them has been run enough. We've proven that they provide effective multi-stage isolation. Each of them does require different services, and they can isolate with either a cemented liner or an open hole completion. So you can do open hole plug and perf. You can do cemented sleeves, and you can divert with multiple or single entry points with each system. So how do we choose the right completion system? So I wanted to highlight just a few of them. There's a lot of them. Like I said, I do actually have a little video series on this. So if you want to know more about some of the benefits and considerations, you can check out those videos for free on the website. But some of the ones that I thought would be a little bit more prominent and relevant for this group, international, outside of the U.S., I wanted to kind of highlight here. So the services required for fracturing, pressure pumping, obviously all three have to have it. Wireline, you've got plug and perf, and coil tubing. You potentially have to have it for plug and perf, and you do have to have it for the coil tubing activated sleeves. So there's additional considerations, though, of just what that means besides just which services are required. Are wireline units available? That can be an issue in some of the developing markets. Also, are perforating guns accessible? So during my time at Baker Hughes, I did a lot of international work and applications for unconventionals. And so in Algeria, they were looking to do plug and perf, but they could not get perforating guns through customs because they flagged it as something different. So all of a sudden, plug and perf was not really available in that market. Also, is the right size coil tubing available? That can be a big factor there. So are the well sites accessible to coil tubing? And do you have a workover rig as a viable alternative if not? So a good international example would be in the Sichuan province in China. Most of those wells are in the mountains. There's very small roads to get up there, very curvy roads as well. So you may not be able to get a large coil tubing up there. And so if you don't have access to coil tubing, that eliminates some options with coil tubing activated systems and with plug and perf if you have to mill out the plugs with the coil tubing and don't have a workover rig available. And then what are the costs of these services? So even within the U.S., there's a lot of variability there. And this was probably 2012, 2013 timeframe. I was doing some comparisons between California and Oklahoma, two different states in the U.S. And at the time, a coil tubing unit was about $40,000 a day in Oklahoma, but it was about $120,000 a day in California. So the price of coil tubing was 3 times higher in California. So that kind of that played a huge factor in the economics of any system that needed to use coil tubing to be able to successfully fracture. So the multi-entry fluid distribution. So we talked about limited entry, we talked about diversion, and some of the options there. But let's look at some of the other consequences and considerations for multi-entry fluid distribution. So once again, back to that basic theory. If you're pumping 90 barrels a minute at surface and through 3 clusters, you're assuming even distribution, you're assuming 30 barrels a minute per cluster. With single entry, because you're only going out of one single exit point, if you're pumping at 30 barrels a minute at surface, then you're distributing all of your fluid and proppant out of that single entry point. as well. So, so much less rate to be able to achieve, much less rate at surface to be able to achieve what you want per cluster. So this is a case history from the Granite Wash in the U.S. So this SPE paper you can see referenced below here. But if we look at of this well, with number of stages, well A was plug and perf with 10 stages with 3 clusters per stage. Well B was 30 coil tubing activated frac sleeves with individual. So overall, both of them have 30 injection points in the well. Their frac spacing was virtually the same, 165 feet. All of their fracturing parameters, there was virtually the same, very little variance until we get to the average frac rate. So if we look at well A, it's 99 barrels a minute. Well B was 40 barrels a minute. Now, if we go back to that basic theory of distribution with plug and perf, 99 barrels a minute through 3 clusters, that means that they were targeting 33 barrels a minute per injection point per cluster. So at 40 barrels a minute per injection point on well B, that's arguably more aggressive of a frac job than the 33 barrels a minute per cluster per injection point that we had on well A. But look at the maximum horsepower required. So well A, because they were pumping at those large volumes, those high rates and high pressures, they required almost 21,000 horsepower, whereas well B, with a less rate in the frac job at surface, they were able to stay under 7,000 horsepower with this job. So, and the way that can play a huge difference with this is overall space on location. So 21,000 horsepower, it depends on which company you're using, what the output of their pumps are and everything else. But generally speaking, each new frac pump, fresh out of the factory, outputs about 2,000 horsepower. Now, over some usage, that goes down, but let's just assume we have a brand new fleet. They're all 2,000 horsepower. Well A is going to require 11 trucks on location, 11 pumps, plus any redundancy. And well B would require 8,000, so 4 trucks to have that 8,000 horsepower capacity there. So if you're in a location where you're on top of the mountains or you just limited on space all the way around, the type of completion, downhole completion that you choose can have a direct impact on what your surface impact is while fracturing the well. Another consideration with that is fluid distribution or height containment. So let's look at this situation here. So you actually see this through multiple plays in the U.S., through multiple plays international, where you've got your target reservoir that you're trying to fracture and produce. Below it here, I'm showing that we have a saltwater bearing zone, and above it, we have another target reservoir that you intend to come back and develop at a later time period. So if we're doing multiple entry, then and we don't have good distribution of our frac, then what happens if you breach out a zone? So the first issue is pretty obvious. If you breach into a saltwater zone, if you create a conductivity there and start producing water, that's taking away from the overall cost of your well, or excuse me, the overall value of your well. And now you're having to deal with salt water and lower production. The second one might not be quite as obvious, but you breach into target reservoir 2, if you get conductivity and you start producing from it, you might even get a good well. You may not even care at the time. But what happens if you come back later to develop target reservoir number 2 and realize that you've depleted it while developing target reservoir 1? Now, overall, you're not going to be able to produce target reservoir number 2 as you were hoping. And it's also probably a pretty decent indication that you did not effectively drain target reservoir number 1 either. So now you've left a lot of hydrocarbon in place in target reservoir number 1. But what if you do single entry? Now, by no means am I saying you have direct control of your height, because at the end of the day, we all know that depends on your rock properties and everything else. But you have indirect control of your fracture height because you're going out of a single entry point. So you do have direct control over how much fluid and proppant is going out of that individual injection point. And if you're monitoring a surface, maybe with microseismic or something like that, then if you see you moving out of zone, then you can try to adjust your frac job accordingly. And then because you're doing that single entry, at least hopefully, and especially if you have a decent idea of how your fracture grows, then hopefully you stay in zone, you avoid any other reservoirs, and more effectively produce your initial target reservoir number one. So, so one of the interesting things when I present these presentations, especially internationally, everybody wants to know which completion system is used the most often in the U.S. And the answer is plug and perf by a large margin right now. So it's probably it's at least 95% of the overall market in the U.S. and it's probably more like 98%. So just kind of some other products being used in specialty applications or niche applications, but that can be a little bit deceiving as well because before the downturn in 2015, plug and perf was still dominant, but it was only probably 60% of the market, give or take. Sleeves were still doing well and things like that. And it's important to realize that there's a lot of dynamics that go behind that besides just overall efficiency. So this is an example from the U.S. Bakken. So, and before I go through the example, let me explain the situation. So before 2015, the state of North Dakota, who controls the minerals and the drilling rights and the rules for oil and gas, they basically said, okay, so once you drill a well, you have 1 year to complete it and put it on production in order to keep your leases and everything. When the downturn happened in 2015, they revised that and said, you can drill the well and you have 2 years now to complete the well, to fracture it, and then to put it on location. Or excuse me, put it on production. So that changed a lot of dynamics there. Now, the other thing that's kind of unique about completions is that you have wellbore construction cost, which goes to the drilling budget, and then you have the actual completion cost, the actual frac job itself, which goes to the completion budget. So we have to think about that. What is the drilling rig using to drill these wells? So casing, you have to have casing on all three completion systems, so there's no real difference there. Oh, and let me clarify one more thing before I start putting these prices up. These are generic pricing. There's a lot of variability here, but these are relatively accurate pricing, especially from a relative standpoint to what we actually experienced here in the U.S. In that 2015 time frame. So if you were to cement a 10,000 foot lateral, it would be about $50,000. If you were to do a 50 stage ball activated frac sleeves, the cost of the frac sleeves, assuming about $3,000 each, would be $150,000. If you're doing open hole, you had to have 50 open hole packers, assuming $3,000 each, about $150,000. If you're doing the coiled tubing sleeves and assuming $3,000 each for them, 50 of those would be $150,000. So what is our actual completion cost that goes with the drilling rig, that goes with the wellbore construction? Let's look at that from a system standpoint per well. So a 50 stage plug and perf would require you to cement the 10,000 foot lateral. So it'd be about $50,000. A 50 stage open hole ball activated system would require the sleeves and the open hole packers, which is about $300,000. 50 stage coiled tubing system, traditional, where it's cemented into place, would be $150,000 for the sleeves, $50,000 for the cement. A 50 stage open hole would be $150,000 for the sleeves, $150,000 for the packers. And then if you were to do a 50 stage open hole plug and perf where you ran 50 packers, then that would be $150,000. So, it's pretty clear with this system that that you see a lot of initial savings. So if you're an operator and you're in the Bakken during this time frame, you're trying to save as much cash as possible. You have to continue drilling wells to be able to hold your leases. Otherwise, you've just wasted a lot of money. But you don't have to actually fracture them until prices improve or 2 years later. So if your strategy is to drill the wells but not complete them, plug and perf is the clear choice here because you're talking about in a matter of 10 wells, you're saving millions of dollars by just cementing a liner into place. Now, the other thing that I don't think was fully intentional, I think it was just a really nice coincidence, is a 50-stage plug and perf job is not a 50-stage plug and perf job. It's a cemented liner. It can be a 75-stage job. It can be a 25-stage job. It's a quote unquote blank canvas for you to do whatever you want to with the well. So if your modern completion design looks different than it did 2 years ago when you drilled the well, then you can simply modify accordingly. Where with every other system, you've already got the sleeves and or the packers in place, and it is what it is. You have a 50-stage system, and there's not a whole lot you can do to adjust that as well. And so, other downturn effects, cash is king. The primary objective was to break even on the well. And, like I said, this trend started in 2015, but as you all know, we've had many dips and, better times and then dips again. 2020, oil crashed again. So all of this has happened repeatedly since 2015. This has actually changed. Services were cheap and readily available up until about this year with supply chain shortages. So yeah, it wasn't a big deal to just get wireline crews out there to get plugs, to get things like that. During these downturns, there's a whole lot less tolerance for failure. People are afraid they'll lose their job because if they choose wrong and it's at least interpreted as $1 million failure because of them, they might lose their job. And it's always a human element, and that a certain level of failure is tolerated with traditional completions. If you've always been doing plug and perf, you're going to have plugs preset. It's not as big of a deal if it doesn't happen too much. If you've been using frac sleeves and you have a failure there, it's okay to have that from time to time. But changing something, not so much accepted. And none of this was necessarily a bad thing. Record initial production during these downturns. But a couple of other things to keep in mind: record amounts of fluid and sand have been pumped into these wells. So, even a frac job today doesn't look anything like it did in 2019, much less 2010. And, the completion strategies today are overall different, which just changes the overall dynamics overall with these types of wells. So like I said, it's don't necessarily look at the numbers of plug and perf being so dominant now, just because there are other variables. And the other big thing is the simultaneous fracturing and the improvements overall. Improvements milling out plugs, improvements with better and cheaper designs of plugs, things like that. So there's a lot more factors than just, it's 98% plug and perf, that must be the best way to go. Oh, and another thing to keep in mind, core acreage is being developed. So anytime we go into a downturn, operators are going to naturally just go to the best of their best acreage, which means that there will be increase in production by default just because it is better acreage being developed, and the tier 2 and tier 3 are not developed as much. So yeah, in conclusion, there's 3 primary types of completions. It really is going to depend on your local economics, your local service situation, just different things like that to determine which one is truly the most effective and the most efficient in your application. So thank you all for tuning in today. We'll open it up for Q&A session here in just a sec. All my contact information is here. Like I said, I'm also full-time with Morph Packers now, so if you have any refracturing questions or queries, feel free to reach out to me with those as well. And otherwise, just check out the website for additional information. So with that, I will open it up for Q&A.
Rafaela, you can go.
We don't have questions now. Does anyone have questions? You can send on chat.
We are waiting for some question here in YouTube. people, I think some people are going to write right now, so we
Okay.
can give them some minutes to prepare this question.
Okay. Well, I guess that's either a really good thing or a really bad thing, right? Either it was so well explained that there's no question, or it was so poorly explained that everybody's confused, right?
Could be, but also we all the transmission is going to be recorded, and some people can see again
Right.
the presentation because yesterday we have some conference that or lectures that start with 20-25 people that see it at live,
Mhm.
but by the end of the day we reach like 70 transmission. So the conference and the lecture are receiving some good attendance, but sometimes there the people are too shy to write.
Yeah, yeah.
So well, if oh,
I think he.
oh yeah. Afternoon. Okay. Or Warren, was you can hear me?
Are you sorry? Are you talking to me?
Yes, I was
Yeah, yeah, yeah.
asking.
I can hear you.
Okay, okay, because I was thinking that my internet cut off.
Oh no, no.
So okay, so I think if there are some people, if the people see the record and have some question, I think it could be possible that can contact with you and answer ask you personally. Right?
Yeah, yeah, absolutely. Yep. So
Okay,
anybody too shy to ask questions or just think of something later, or you're watching the recording, don't hesitate to reach out.
okay. So Aaron, thanks for your excellent presentation. I bet that of all the people that was watching the lecture like it a lot. I like it really. So I think we can uh, say thanks for all the time that you have for us. We are waiting to do some activity for the future also.
Okay. Yeah, sounds good.
Okay. So have a good day and thanks guys for the assistance. And don't forget to follow our social media, Instagram SPUnicam. For the last activity for the day, will we have the round table about women in different uh, different works in industry. So thanks for you. Thanks, Ero, again. Rafaela, you can put the video to the sponsor videos.
Okay, thank you, guys.
All right. Just to confirm, I sign off now.
Oh, Rafaela can do it. That.
SNF, for easy, cost-efficient, and sustainable EOR solutions. In a world where the energy demand continues to climb, oil extraction must be done in an environmentally responsible way. For EOR operations, this means reducing CO2 emissions. When changing from water flood to polymer flood, the water production can be reduced from 9 barrels of water to 3 barrels of water per produced barrel of oil. SNF achieves this with modular plug-and-pump installations for quick and cost-effective unit implementation with many added benefits. Polymer flooding involves increasing the viscosity of injection water to enhance sweep efficiency and ultimate recovery of oil within a deposit. SNF assists clients through every step of the process, from assisting screening and reservoir studies, polymer logistics, to on-site storage, mixing, and injection. SNF designs, implements, and operates on-site facilities for the client. Polymer flooding has a higher added value than water flooding. Due to the greater sweep efficiency of polymer flooding, the overall recovery will be accelerated with significant water production reduction per barrel of oil. Using SNF system, clients' water cut went from 90% to 70%, which means 3 times less water production per extra produced barrel of oil, savings on lifting operation and production costs. These benefits also result in a reduction of up to 3 times in greenhouse gas emissions during the operations. SNF improves the efficiency of oil production processes. Because polymer flooding is easy to implement and more mature than other methods, development time will be significantly reduced.